Have you ever wondered how engineers design, everything from the perfect shape for a fish swimming to a jet slicing through the air? Especially when the math describing how fluids move is just notoriously complex, almost impossible to solve directly.
Oh, absolutely. It's like trying to track every single water molecule in a river as it flows downstream.
Yeah.
For any real-world situation, that's just computationally impossible. You'd need, well, a supercomputer bigger than the planet.
Exactly. Welcome to the deep dive. Today, we're plunging into the fascinating world of fluid dynamics. We're exploring how experts navigate those really intricate Navier-Stokes equations by using, well, some incredibly clever shortcuts, what they call approximations.
Right. And you've given some really rich source material here, packed with these complex concepts and equations. Our mission today is to carefully unpack them, pull out the most crucial bits of knowledge, the key insights. We want to offer you a direct shortcut to understanding why these simplifications are used, and maybe more importantly, when they're not just useful, but absolutely essential for predicting how fluids actually behave in the real world.
Okay, let's start there. The full Navier-Stokes equation. That's the foundation, right? The mathematical description of fluid motion. It's where you'd ideally start for an exact solution.
If you could solve it, yes. But for most practical problems, it just becomes unmanageably difficult quickly.
So how do scientists and engineers even tackle that challenge then?
Well, they turn to what are generally called approximate solutions. Now, these don't try to wrestle with the full complex equation. Instead, they start with a simplified form of the Navier-Stokes equation right from the beginning.
Okay, simpler sounds good.
It is, but here's the really critical catch. If the approximation you choose isn't appropriate for the specific flow situation you're looking at, your solution will be completely wrong.
Wrong, even if the math is done correctly.
Totally wrong. Physically incorrect. Imagine using an approximation meant for, say, super slow, thick, syrupy flow when you're actually modeling a high-speed jet wing. You'd get results that are just nonsense, physically impossible.
Yay. Right, so how do you even know which approximation to pick? It sounds like a bit of a minefield. You could easily grab the wrong tool for the job.
That is a fundamental challenge.
Yeah.
And it gets trickier because a particular approximation might be perfect for one region of a flow field.
Ah, just one part.
Exactly. But totally unsuitable for another part of the same flow. Think about water flowing from one big tank into another through a pipe.
Okay.
Way back in the supply tank, far from the pipe entrance, the water's pretty much still, right? So maybe a fluid statics approximation works there.
Makes sense. Almost no movement.
But then, as the water speeds up near the pipe entrance, or where it interacts with the pipe walls, or where it exits into the second tank, you need entirely different approximations for those regions. Maybe irrotational flow near the entrance, boundary layer theory inside the pipe.
Wow, okay, different physics dominating in different places. So what's the secret then? How do you figure out where and when to apply these different shortcuts?
The key, the fundamental technique, is to compare the orders of magnitude of the various terms, the various forces within the equations of motion.
Orders of magnitude. Sounds technical.
It is a bit, but the idea is simple. You're asking which physical effects are dominant in this specific region, which forces are huge, and which ones are so tiny in comparison that we can, probably ignore them without losing too much accuracy.
Okay, that makes conceptual sense, but how do you actually compare, say, pressure forces with viscous forces or inertial forces when they all have different units? It feels like comparing apples and oranges, or maybe kilograms and meters per second squared.
That's exactly the problem. And the solution is a really powerful technique called non-dimensionalization.
Non-dimensionalization, okay.
What it does is strip away all the units. You define some characteristic scales for the problem, like a typical length, maybe the diameter of the pipe, or a characteristic speed, like the average flow speed. You use these reference values.
It's like a ruler for the flow.
Sort of, yeah. You use them to normalize all the variables in the equation: length, speed, pressure, time. Everything becomes dimensionless, just a ratio.
And when you do that?
When you do that, the equations transform. And suddenly, the relative importance of all the different terms, inertia, pressure, viscosity, gravity, unsteadiness, it all boils down to the relative sizes of a few specific dimensionless parameters that pop out of the math.
Ah, so these are the famous numbers like Reynolds number.
Exactly. For the Navier-Stokes equation, you often get four key ones. The Reynolds number, which compares inertial forces to viscous forces. There's the Euler number, relating pressure to kinetic energy. The Froude number, which involves gravity's effect on free surfaces. And the Strawhal number, which tells you about unsteady effects, like oscillating flows.
And these are crucial for experiments too, right? Like testing a scale model in a wind tunnel.
Absolutely critical. For your wind tunnel model to accurately represent the full-size airplane, you need what's called dynamic similarity. And achieving that usually means matching all the relevant dimensionless numbers, Reynolds, maybe Strohel if it's unsteady, etc., between the model and the prototype.
That ensures the fluid behaves proportionally.
Precisely. But the good news is, often conditions allow for simplification. For instance, if your flow is steady, meaning it's not changing over time, then the time-dependent terms drop out and the Stroll number just becomes zero. It's irrelevant for that specific problem.
Okay, that simplifies things. What about gravity? That seems like it would always be important.
It depends. For many flows without a free surface, think of completely full pipe flow or airflow around an airplane, or a submarine deep underwater where there's no air-water interface nearby.
Right, no waves or sloshing.
In those cases, gravity's only dynamic effect is basically just the hydrostatic pressure, variation pressure, increasing with depth. And we have a clever trick for that. We can define something called a modified pressure.
Modified pressure, what's that?
It's basically the regular pressure plus the hydrostatic term, Riggs S. By defining this new variable, P prime, we can rewrite the Navier-Stokes equation in a way that the explicit gravity term disappears.
Ah, you absorb it into the pressure term.
Exactly. And by doing that, the Fruta number, which represents gravity's influence, drops out of the list of relevant parameters for these types of flows. This is super useful, especially in computational fluid dynamics, or CFD, because it lets you separate the gravitational effects from the other dynamic pressure effects.
Clever. But I guess you can't always use that trick.
Absolutely not. You must not use this modified pressure if your flow does have a free surface. Think waves on the ocean, flow over a dam, water sloshing in an open tank. In those cases, gravity is dynamically crucial in shaping the free surface, and the Fruta number is essential. You can't hide gravity then.
Okay, got it. So let's dive into one of the really interesting extremes. You mentioned approximations for specific situations. What about creeping flow, also called Stokes flow, right?
Yes, creeping flow, or low Reynolds number flow. This is where things get really, really weird and non-intuitive for us humans. It occurs when the Reynolds number is tiny, much, much less than 1.
Re1. So super low speeds, or very small objects, or incredibly thick, viscous fluids.
Exactly. You see it when you pour honey or thick syrup really slowly. That's creeping flow. The viscosity, the stickiness, just completely dominates everything else. Inertia is basically negligible.
Okay, honey makes sense. But you mentioned surprising examples.
Yes. The most fascinating examples are happening all around us and even inside us, but we can't see them directly. It's the flow around microscopic organisms.
Microbes, like bacteria.
Precisely. Think of a salmonella bacterium. It's maybe only a micron long, incredibly tiny, even though it's swimming in water, which doesn't feel very viscous to us at our scale.
Right, water feels pretty thin.
But for that tiny bacterium moving slowly, the Reynolds number is extremely low. For that microbe, water feels incredibly thick and syrupy. Viscosity is king in its world.
Wow. So if viscosity is king, what's the main outcome of this creeping flow approximation? What does it do to the Navier-Stokes equations?
It throws out all the inertial terms. The terms involving acceleration and density just vanish from the momentum equation.
Density vanishes completely.
Completely drops out as a parameter in the governing equation itself.
Okay.
This is one of the most mind-bending aspects. The equation simplifies dramatically to basically pressure forces, balancing viscous forces. It becomes something like gradient of P is approximately μ times Laplacian of V. Density isn't in there.
That is weird. So no inertia, no density dependence in the equation. What does that mean for how these tiny organisms actually move? We swim by pushing water back, and our inertia carries us forward, lets us glide.
There's no gliding in creeping flow. Zero. Because there's negligible inertia. The instant a microorganism stops actively propelling itself, it stops moving. Instantly.
Hitting the brakes.
Exactly. Think of a sperm cell. It has to constantly undulate its tail, its flagellum. The very moment the tail stops wiggling, the sperm stops dead in the water. It can't coast. To move forward, it has to continuously work against the overwhelming viscous forces.
It's really hard to imagine a world without inertia like that. Is there a human scale analogy?
It's tough, but forget swimming in honey that still has some inertia. A better, though maybe stranger analogy is, imagine a child trying to swim in a giant ball pit. a pool filled with plastic spheres.
Okay.
If the child tries to thrash around, the instant they stop moving their arms and legs, all motion ceases. The balls just stop them. There's no glide, no momentum carrying them forward. They have to constantly actively work just to inch forward. That's kind of like how a bacterium experiences water.
That's a great visual. And the other point, density disappearing from the equation. What's the impact of that? Because normally, for a car or a plane, drag definitely depends on air density, right? That's an inertial effect.
Absolutely.
Yeah.
At high Reynolds numbers, aerodynamic drag is strongly dependent on density. More density, more drag. But in creeping flow, because inertia is negligible, the drag force cannot even be a function of density.
So what does it depend on?
It depends only on the fluid's viscosity,
Yeah.
the characteristic speed, b, and some characteristic length scale of the object.
Yeah.
The drag force is typically proportional to Mach times v times L. For a perfect sphere, the constant of proportionality is 3 pi, giving Stokes' famous drag law. Fd equals 3 pi mu Vd, where d is the diameter. No density anywhere in sight.
Can you give a concrete example where this lack of density dependence is really noticeable?
Sure. Think about a tiny volcanic ash particle falling through the atmosphere after an eruption. It's very small, falls relatively slowly, so it's in the creeping flow regime. It quickly reaches a terminal velocity where the drag force balances its weight. If you calculate that terminal velocity using the creeping flow approximation, you find it's nearly independent of the air density. It depends strongly on the particle size, its weight, and the air's viscosity, but hardly at all on the air's density.
So as it falls from high altitude where the air is thin down to sea level where the air is much denser.
Its falling speed barely changes, which is counterintuitive, right? You'd think denser air would slow it down more. But in creeping flow, density doesn't play that role in drag. Viscosity does.
Okay, so that's the strange world of creeping flow. Viscosity rules, inertia rules, density disappears. Now let's swing completely the other way. Let's talk about high Reynolds numbers and this idea of invisid flow. There's often confusion here, isn't there?
Yes, quite a bit. The term invisid flow can be misleading because, as you said earlier, all real fluids that engineers care about do have viscosity. You can't just wish it away.
So what does invisid flow actually mean in practice?
It refers to regions of a flow field where the net effect of viscous forces is negligible compared to other forces, like pressure forces or inertial forces. This typically happens at high Reynolds numbers, the opposite of creeping flow.
So not zero viscosity, but negligible effects of viscosity.
Exactly. Think of it as areas where the fluid is moving fast, or the object is large, or the viscosity is low enough that friction effects are just overwhelmed by the momentum and pressure changes. Maybe a better term is invisid regions of flow.
Okay, invisid regions. And when you make that approximation, assuming viscous forces are negligible, what happens to our friend, the Navier-Stokes equation?
It simplifies quite nicely. The term involving viscosity, 1 times the Laplacian of V, just drops out. What you're left with is called the Euler equation.
The Euler equation? And where is this valid?
It's generally appropriate in high Reynolds number regions, but specifically away from solid boundaries, walls, and also away from the turbulent wakes that form behind objects.
Why away from walls and wakes?
Because near walls, the fluid velocity has to slow down rapidly to 0 right at the wall. That's the no-slip condition. This creates very large velocity gradients, and large gradients mean viscous forces become very important. They can't be neglected there. Same thing in the wake, where there's lots of shearing and turbulence.
So the Euler equation has a big limitation then. It can't handle the no-slip condition at walls.
Precisely. That's its Achilles heel. The Euler equation inherently allows fluid to slip along a solid surface, which we know doesn't happen in reality. Fluids stick.
Okay, so if Euler works in these outer regions, how does the famous Bernoulli equation fit in? I know that's often linked to invised flow.
Right. Bernoulli's equation, which states that the sum pro plus V22 plus G's is constant, can be derived from the Euler equation. So in these inviscid regions of flow, Bernoulli's equation holds. But there's a catch in its most general form derived from Euler.
What's the catch?
The constant C in the Bernoulli equation, Profode plus V22 plus GZ equals C, is only guaranteed to be constant along a specific streamline. It can actually have different values on different streamlines if the flow is rotational.
Rotational, meaning the fluid particles themselves are spinning.
Yes. Even if the flow is inviscid, no net viscous forces, it can still be rotational. A classic example is solid body rotation. Imagine water in a cylindrical bucket spinning at a constant rate, like a solid chunk of ice.
Okay, all moving together.
There's no viscous shear between layers because they're all moving together, so it's effectively inviscid. But every fluid particle is rotating. In that flow, The Bernoulli constant C does change as you move from a streamline near the center to one near the outer edge.
Interesting. So invisid doesn't automatically mean irrotational. That leads us nicely to the next big approximation. Irrotational flow, sometimes called potential flow. What's the deal here?
This is another really elegant and powerful simplification. An irrotational region of flow is one where the individual fluid particles have no net rotation. Their vorticity, which is a measure of local spinning motion, is essentially zero.
And how does this relate to invisid flow?
Often the invisid regions we just talked about, far from walls and wakes and high Reynolds number flow, are also irrotational. But as the spinning bucket example showed, an invisid region can be rotational. Irrotational is a stricter condition.
Okay. And what's the mathematical magic that happens if a flow is irrotational?
This is the beautiful part. If a flow is irrotational, the velocity vector field can be expressed as the gradient of a single scalar function. We call this function the velocity potential, usually denoted by the Greek letter phi. So v, free.
Hang on. Instead of needing 3 separate equations for the velocity components, u, v, w, you can describe everything with just one scalar function, phi.
Exactly. Think about it. You combine 3 unknown velocity components into just one unknown scalar variable. This is a massive simplification. When you combine this VH with the continuity equation, which basically says mass is conserved, you often end up with a single, well-known partial differential equation for Laplace's equation.
Laplace's equation, I've heard of that. It shows up everywhere in physics.
It does, and we know a lot about how to solve it. Once you solve for phi, you can easily find all the velocity components just by taking derivatives. Irreversir to a u, a raised to s. It eliminates 2 of the equations you'd normally need.
That sounds incredibly useful. And this potential flow solution, what kind of fluids does it work for? Does viscosity matter? Density?
Here's the kicker. The solution based on A0 is valid for any incompressible fluid, regardless of its density or viscosity, provided you're in a region of the flow where the irrotational approximation is appropriate. It even works instantaneously for unsteady flows.
Wow. And what about Bernoulli and irrotational flow? Is it still just constant along streamlines?
This is another huge advantage. Because the flow is irrotational, it turns out the viscous term in Navier-Stokes, MEV, also vanishes mathematically for a different reason than in general invisid flow. You still end up with the Euler equation. But crucially, when the flow is irrotational, the Bernoulli equation simplifies further. The constant C, Pro plus V22 plus GZCC, is now constant everywhere throughout the entire irrotational flow region, not just along individual streamlines.
Everywhere. That's much more powerful.
Immensely powerful for calculations.
And I remember reading that because Laplace's equation is linear, you can add solutions together. Superposition.
Yes, exactly. Since Laplace's equation is linear and homogeneous, any sum of individual solutions is also a solution. This is called superposition, and it's like having fluid dynamics Lego blocks.
Lego blocks, yeah.
You can take simple, known, elementary irrotational flows and add them together to build up more complex and realistic flow patterns. The velocity at any point in the combined flow is just the vector sum of the velocities from the individual building blocks you used.
Okay, what are some of these elementary building blocks?
The simplest is just a uniform stream flow moving steadily in one direction. Then you have things like a line source or a line sink, where fluid appears to flow uniformly outwards from or inwards towards a line. There are mathematical singularities right at the source sink line, but they're useful building blocks.
Like a drain.
Sort of, yeah. Or the opposite, like a sprinkler pipe. Then there's a line vortex, where fluid swirls around a central line. Interestingly, the math for a line vortex is kind of the flip side of the math for a line source.
Yeah.
And another important one is the doublet, which you get by imagining a source and a sink of equal strength getting infinitely close together.
Okay, uniform stream, source sink, vortex, doublet. How do you use these Legos to model something real?
Let's take a tornado, or at least a simplified model of one. If you look at a horizontal slice, you can often model the outer region, far from the center, as an irrotational vortex, potential flow. The very core, however, might be better modeled as solid body rotation, which we said is invisid but rotational. By patching these two models together, you can calculate the pressure distribution.
And what does that show?
It correctly predicts that the pressure drops as you get closer to the center in the outer irrotational region and reaches its absolute minimum right at the very center of the core, the eye of the storm.
That's cool. What's another classic example of superposition?
A really famous one is modeling the flow around a circular cylinder. If you take a uniform stream and superimpose a doublet right at the origin, oriented against the stream.
Okay, uniform flow plus a doublet.
The resulting combined flow pattern has streamlines, And remarkably, one specific streamline forms a perfect circle.
A circle just appears out of the math.
Exactly.
Yeah.
And because any streamline in potential flow can be thought of as a solid boundary, since no fluid crosses it, you can just say, okay, that circular streamline is the surface of my cylinder. And voila, you have the potential flow solution for flow over a circular cylinder.
What does that solution look like?
It shows the flow splitting smoothly around the cylinder. It predicts two stagnation points, one right at the front, the nose, and one right at the back, the tail, where the fluid velocity is exactly zero. These are points of maximum pressure. It also predicts that the fluid speed reaches its maximum value right at the top and bottom of the cylinder, where it's exactly twice the speed of the oncoming uniform stream.
This potential flow theory sounds incredibly elegant, almost magical, but there must be a catch. It sounds too good to be true.
There is a very famous catch. It leads to something called D'Alembert's paradox.
D'Alembert's paradox, I remember you mentioning that. What is it?
Back in 1752, D'Alembert used this potential flow theory and proved mathematically that for any non-lifting body of any shape placed in a steady, uniform stream, the net aerodynamic force predicted by the theory is zero drag.
Zero drag, but that's obviously wrong. Everything experiences drag when it moves through air or water.
Precisely. That's why it's a paradox. The elegant theory predicts something that flatly contradicts reality. We know planes need engine thrust to overcome drag, cars use fuel to fight air resistance.
So why does the paradox happen? Where does the potential flow approximation break down so badly?
It breaks down exactly where we said the Euler equation breaks down, near the solid surfaces and in the wake behind the body. Potential flow theory cannot satisfy the no-slip condition at the wall. It assumes the fluid slips frictionlessly past the surface.
So it ignores viscosity right where viscosity is actually most important at the boundary.
Exactly. That slip at the wall means it doesn't capture the friction drag. It also messes up the pressure distribution, particularly on the rear side of the object, because it doesn't predict the flow separation and wake formation that happens in real flows, which is the main source of pressure drag, or form drag.
But even though it predicts zero drag, you said potential flow can still give useful insights. You mentioned fish design.
Yes, remarkably, even though it gets the drag wrong, the pressure distribution predicted by potential flow away from the immediate vicinity of the wall and wake can be surprisingly accurate, especially on the front part of a smoothly shaped body. Engineers use it for initial estimates, and biologically, fish seem to evolve to take advantage of these potential flow pressure fields.
How so?
Well, fish often have their eyes located near the stagnation point at the nose, where pressure is high, but velocity changes are small, which might minimize vision distortion. And their gills are often placed further back, near the shoulders of their body shape, where potential flow predicts lower pressure, higher speed. This suction pressure might actually help the fish to exhale water through the gills, especially when swimming fast.
That's fascinating. Nature exploiting ideal fluid dynamics. And you also mentioned that idea that any streamline can be treated as a wall. How else is that used?
It's a very powerful modeling technique. Say you want to model wind flowing over a smoothly shaped hill. You can often find a potential flow solution, maybe by combining a uniform stream with a source or doublet, where one of the streamlines has the approximate shape of the hill. You then just treat that streamline as the ground surface.
Clever. And the vacuum cleaner example.
Right. You can model the suction nozzle of a vacuum cleaner near the floor as a line sink in 2D potential flow. Fluid flows into the sink, but that would allow flow to come through the floor, which is unphysical.
So how do you fix that?
You use the method of images. You place an identical image sink symmetrically below the floor level in your model. When you superimpose the flow from the real sink and the image sink, the streamline corresponding to the floor level becomes perfectly flat, horizontal. No flow crosses it.
So the floor becomes a streamline automatically.
Exactly. It satisfies the boundary condition of no flow through the floor. And this combined model correctly predicts that the maximum suction, lowest pressure, highest speed, along the floor doesn't occur right under the nozzle, but slightly offset from it.
Okay, so potential flow is elegant, useful for building complex flows, great for pressure away from walls, but fails on drag and the no-slip condition. This seems to lead us directly to the need for something else, something that handles the wall interaction properly.
Precisely. All these issues, the inability of Euler potential flow to handle no slip, the prediction of zero drag, the failure to capture flow separation pointed to a missing piece. And that piece was brilliantly provided by Ludwig Prandtl in 1904 with his boundary layer theory.
Prandtl's boundary layer. This feels like a really central concept.
It is arguably one of the most important concepts in 20th century fluid dynamics. Prandtl proposed a way to bridge what he called the huge chasm between the ideal fluid theories, like potential flow, and the reality of viscous fluids obeying the full Navier-Stokes equations, especially near surfaces.
And how did he bridge that chasm?
He had this revolutionary insight. For high Reynolds number flows, where invisid theory works away from surfaces, the region where viscous effects are significant is confined to a very thin layer right next to the solid surface. He called this the boundary layer.
So split the flow into two zones.
Exactly. An outer flow region, away from the body, where you can still use the simpler invisid equations like Euler or potential flow, and then this thin boundary layer region stuck to the wall, where viscosity is dominant and absolutely cannot be ignored. Here, the fluid velocity transitions rapidly from zero at the wall, no slip, up to the velocity of the outer flow at the edge of the boundary layer.
And the crucial assumption is that this boundary layer is really, really thin.
Yes, that's key. The assumption is that for high Reynolds numbers, the boundary layer thickness, usually denoted by delta, is very small compared to the characteristic length of the body, like the length of a wing cord, x. So x.
Does the thickness depend on the Reynolds number?
It does, strongly. For laminar flow over a flat plate, the boundary layer thickness grows roughly as the square root of the distance downstream, and it scales like dex is proportional to 1 divided by the square root of the Reynolds number based on x, rex.
So higher Reynolds number means?
Thinner boundary layer, which makes sense. At higher speeds or lower viscosities, the inertial effects confine the viscous influence to an even narrower region near the wall.
Okay. And these boundary layers aren't always smooth and predictable, are they? They can become turbulent.
That's right. A boundary layer typically starts out as laminar, smooth, orderly, layered flow. But as it develops downstream along a surface, it can become unstable and transition, first into a messy transitional state, and finally into a fully turbulent boundary layer.
Turbulent meaning chaotic and mixed.
Highly chaotic, with swirling eddies and intense mixing across the layer. This transition usually happens when the Reynolds number, based on distance, rex, exceeds a certain value, maybe around 500,000 for a flat plate, though it depends on surface roughness and disturbances. Sometimes engineers even intentionally trip the boundary layer using small wires or roughness near the start.
Why would they want turbulence?
We'll get to that. It has some surprising benefits. But first, let's talk about another simplification within the boundary layer itself: pressure.
Right, you mentioned pressure across the boundary layer is nearly constant. That sounds counterintuitive.
It does, but it's a remarkably accurate approximation. Because the boundary layer is so thin, x, the streamlines within it have very little curvature in the direction normal to the wall. If there's negligible curvature, there's no significant centripetal acceleration required in that direction, and therefore no significant pressure gradient needed to provide it. So the pressure change across the boundary layer in the A direction, perpendicular to the wall, is practically zero. EO, zero.
So the pressure at the wall is essentially dictated by the pressure just outside the boundary layer in the outer invisid flow.
Exactly. This is a huge simplification. It means we can often calculate the outer invisid flow first, using potential flow theory, for instance, find the pressure distribution along the edge of where the boundary layer would be, and then impose that pressure distribution onto the boundary layer calculation itself. It decouples the pressure field determination.
And this simplifies the governing equations within the boundary layer, too.
Dramatically. Prandtl took the full Navier-Stokes equations and systematically threw out terms that were small specifically within this thin layer, based on the NX assumption. The resulting boundary layer equations are much simpler than the full Navier-Stokes.
How are they simpler to solve?
One key difference is their mathematical character. The full Navier-Stokes equations are elliptic, meaning information travels in all directions, making them complex to solve numerically. But the boundary layer equations become parabolic in the main flow direction.
Parabolic. What does that mean practically?
It means that flow information primarily travels downstream. Disturbances don't propagate significantly upstream within the boundary layer approximation. This allows for much more efficient numerical solutions. You can essentially march your calculation step by step downstream from the starting point without needing to know what happens far ahead. You only need boundary conditions at the start, at the wall, and at the outer edge, not at the downstream end.
Ah, that sounds much easier computationally. And this led to famous solutions. You mentioned Blasius?
Yes, the Blasius solution is a classic early result for the laminar boundary layer on a flat plate with zero pressure gradient, uniform outer flow. It's a similarity solution, meaning the velocity profile shape, when scaled properly, is the same everywhere along the plate. And the crucial thing was, Lassius's calculated profile showed stunning agreement with experimental measurements. It was a huge validation of Prandtl's theory.
So we can calculate these velocity profiles inside the boundary layer. But since it's so thin, how do we quantify its overall effect on the flow? I think you mentioned displacement thickness.
Right. Even though the boundary layer is thin, it does affect the outer flows slightly. Because the velocity is slowed down near the wall, the streamlines just outside the boundary layer have to move outwards slightly to accommodate the same mass flow rate. The displacement thickness, delta star, quantifies this outward shift.
So it's like the wall appears slightly thicker to the outer flow.
That's a great way to think about it. Delta star represents an apparent increase in the thickness of the body, as perceived by the outer invisid flow. For a laminar flat plate, is roughly 1/3 of the total boundary layer thickness.
And why is this useful?
It allows you to refine the outer flow calculation. For example, if you have flow entering a channel, the boundary layers grow on the top and bottom walls.
Yeah.
This growth, represented by mass of dou, makes the effective channel width narrower downstream, causing the core flow in the middle to accelerate, even if the channel walls are physically parallel. You need to account for Gauge to get the core flow right, which is critical in designing things like wind tunnel test sections or engine inlets.
Makes sense. And there was another thickness, momentum thickness.
Yes, momentum thickness, usually theta. This one quantifies the loss of momentum flux in the flow due to the presence of the boundary layer. Remember, the fluid near the wall is slowed down, meaning it has less momentum than the outer flow. Theta represents the thickness of a hypothetical layer of outer flow fluid that would carry this missing momentum. It's directly related to the friction drag on the surface.
Okay, displacement and momentum thickness help quantify the boundary layer's impact. Now, back to laminar versus turbulent boundary layers. You said turbulent ones are thicker.
Generally, yes. Turbulent boundary layers are significantly thicker than laminar ones at the same Reynolds number, but they also have a very different velocity profile shape.
How so?
A turbulent profile is much fuller, meaning the velocity increases very rapidly right near the wall and then stays relatively high across most of the layer. A laminar profile is more gradual and rounded. The steeper slope near the wall in a turbulent boundary layer means higher wall shear stress, more friction drag.
More drag. That sounds bad. So why did you say turbulence can be beneficial?
Because of flow separation. That fuller profile, with more high momentum fluid closer to the wall, makes turbulent boundary layers much more resistant to separating from the surface, especially when facing an adverse pressure gradient, where the outer flow is slowing down.
Ah. And that explains the golf ball dimples.
Exactly. The dimples are roughness elements designed to intentionally trip the boundary layer, forcing it to become turbulent much earlier than it would on a smooth sphere.
So it creates more friction drag initially?
Yes, slightly more skin friction drag. But the huge benefit is that this turbulent boundary layer stays attached to the back of the ball much longer before separating. On a smooth ball, the laminar boundary layer separates very early, creating a massive low-pressure wake behind it. This large wake causes enormous pressure drag, form drag.
And on the dimpled ball?
The turbulent boundary layer delays separation, resulting in a much smaller wake and drastically reduced pressure drag. The reduction in pressure drag far outweighs the slight increase in friction drag, leading to significantly less overall drag and allowing the dimpled ball to fly much farther.
That's a fantastic example of exploiting boundary layer characteristics. How do these pressure gradients, favorable and adverse, affect the boundary layer shape more generally?
When the outer flow is accelerating, dpdx0, dgux0, that's a favorable pressure gradient. It helps keep the boundary layer energized and attached, leading to those stable, rounded velocity profiles. But when the outer flow is decelerating, dpdx0, dudx0, that's an adverse pressure gradient. This pushes back against the slow-moving fluid near the wall.
And that's what leads to separation.
Yes. An adverse pressure gradient causes the velocity profile to develop an inflection point, a change in curvature.
Yeah.
If the adverse gradient is strong enough, it can actually cause the velocity gradient right at the wall, at y0, which is proportional to the wall shear stress, to become zero or even negative.
Zero shear stress, that's the separation point.
That's the definition of the separation point. The flow right at the wall stops moving forward, and downstream of that point you get flow reversal near the wall, lifting the boundary layer off the surface and creating a recirculating separation bubble, or wake. The boundary layer equations themselves actually break down at and beyond the separation point.
Can you visualize that difference, laminar and versus turbulent separation?
Sure. CFD simulations often show this clearly. If you simulate flow over a curved bump, a laminar boundary layer might easily separate on the downstream side where the flow decelerates due to the adverse pressure gradient. But if you run the same simulation with a turbulent boundary layer model, it often stays attached much further along the bump, or might not separate at all, again highlighting its greater resistance.
And there are ways to approximate these boundary layer features without solving the full PDEs.
Yes, there are integral methods, like the Kármán momentum integral equation. These use control volume analysis on the boundary layer to get approximate results for things like boundary layer thickness and wall shear stress, often much faster than solving the partial differential equations, though usually less accurately.
Okay, this has been a fantastic tour of the approximations. Let's quickly circle back to that application spotlight you mentioned, droplet formations, say, for inkjet printing. How do these different ideas connect there?
Right, it's a great example because different approximations might be relevant at different stages or under different conditions. For instance, if the pressure pulse used to eject the droplet is very rapid.
Like a really sharp kick.
Exactly. For that initial extremely fast acceleration, the time might be too short for viscous effects near the walls of the nozzle to become significant. In that very specific transient scenario, the potential flow approximation can actually be quite useful for predicting the initial shape and velocity of the fluid exiting the nozzle.
Potential flow, even though it's a viscous fluid in a small channel.
Yes, because the timescale is so short, the viscosity doesn't have time to act significantly across the whole flow. This applicability is often indicated by certain dimensionless numbers used in droplet dynamics, like a small Onnesauge number. A small Onnesauge number basically says that inertial and surface tension effects are dominating over viscous effects during the initial formation.
So surface tension and inertia shape the start. Viscosity maybe matters more later as it pinches off.
Precisely. It beautifully illustrates how you might use potential flow for the initial ejection, but then perhaps need to consider viscosity and the full Navier-Stokes, or approximations like boundary layer theory if relevant, to understand the droplet's later evolution, pinch-off, and oscillation. Different tools for different parts of the problem.
So reflecting on this whole journey, we started with the incredibly complex full Navier-Stokes equations, almost unsolvable for most real problems.
And we saw how clever approximations provide a way forward. We dove into creeping flow, that strange low Reynolds number world where viscosity dictates everything, inertia vanishes, and density becomes irrelevant, completely changing how microscopic life navigates.
Then we explored the other extreme, invisid and irrotational flow. We learned how potential flow lets us build complex patterns from simple blocks using superposition, giving insights into pressure fields, but also leading to the famous D'Alembert's paradox of zero drag.
Which highlighted the crucial role of viscosity near surfaces, leading us finally to Prandtl's boundary layer theory. That brilliant concept bridges the gap, dividing the flow into an outer invisid region and a thin inner viscous layer explaining friction, separation, and why golf balls need dimples.
The real beauty here, it seems, isn't just simplifying the math, though that's obviously crucial. It's how these approximations let us isolate and understand the dominant physical forces at play in wildly different situations.
Absolutely. Whether it's viscosity overwhelming everything for a bacterium, or inertia and pressure shaping the flow around an airplane wing, or surface tension battling inertia in droplet formation, knowing when and where each approximation is valid gives us incredible insight. It distills the essential physics.
So the next time you watch a fish glide seemingly effortlessly, or feel the pull of a vacuum cleaner, or even see syrup slowly dripping, maybe pause and consider the hidden world of fluid dynamics approximations at work underneath it all. What other everyday phenomena, maybe ones you haven't thought about, could be explained by understanding these powerful shortcuts in fluid mechanics?